All right, hey everybody, it's Mr. Jones. We're going to be doing the video lecture that goes over Activity 11, a summary of molecular polarity and intermolecular forces. So if y'all would flip to page 11 of your Unit 3A packet. It's right after the molecular geometry and right before Activity 12, which is the practice putting it all together. So we're going to define polarity and intermolecular forces and do some practice examples with each of those as well. So polarity is just how atoms share electrons, or how molecules share electrons. If a molecule is nonpolar, that means it has equal sharing of its electrons around the entire molecule. If a molecule is polar, it has unequal sharing of electrons. And a molecule is polar if there's a lone pair on the central atom, or if the atoms are bonded to the central atom are different. So that's kind of a quick, ugly explanation, but we'll go through a couple practice problems and you should get a better idea of what polarity looks like. So here's some examples. Nonpolar molecules over here on the right of this line are things like N2, nitrogen, two nitrogens. So those nitrogens are pulling that way, those nitrogens are pulling that way. They're pulling in the exact same way, so they're equally sharing electrons. Same thing with CO2. Oxygen pulls that way, oxygen pulls that way, away from the central atom, so there's equal sharing on both sides. With CCl4, you have one pulling up, you have one pulling right, one pulling down, and one pulling left. So we have equal sharing of those electrons on all sides. They're all pulling in the same way, and ultimately everybody is sharing electrons equally. In polar molecules, you're going to have some difference of strength. So there's something like H2O where oxygen is pulling electrons towards itself because it is much stronger than those hydrogens. And it's doing so at an angle. There's also lone pairs around these oxygens, and so there's going to be unequal negativity surrounding that oxygen. Same thing with HCl. Cl is capable of pulling electrons toward it much, much stronger than hydrogen is. And so it's unequal. They're mostly going around the chlorine. And something like NH3 even, or CH2Cl2, but we'll do NH3 because it's on here. NH3, where nitrogen is pulling the bulk of electrons towards itself, and they're unequal. There's going to be a slightly positive charge on the hydrogens, a slightly negative charge on all the oxygens. Now we'll walk through a couple examples, and ideally you'd quiz yourself, but we'll just kind of walk through each of these. So polarity practice. First, we've got HBr. If we draw these out, we have two different atoms, so they're going to share electrons unequally. Bromine has much higher electronegativity, so it's going to pull a lot more electrons towards it than hydrogen is. We've got one thing going in one way, so this is going to be polar. Next, we've got H2. The two atoms are the same, and so they're going to pull electrons towards each other with the exact same strength, meaning this is nonpolar. Another one, NH3. We see a lone pair on the nitrogen, and so we've got a charge moving. Nitrogen is more electronegative, so we see pull that way, that way, that way, and we see a lone pair. Anytime you see a lone pair, you know that there's polarity, unequal sharing, because nitrogen is a lot more negative than the hydrogens, which are all slightly going to be positive. Next, BF3. This is an interesting one because there is no lone pair on boron. Boron is happy with an incomplete octet. So even though we're being pulled in multiple different directions, actually this is all going to be pulled in the same way, and there is going to be equal sharing in this. It's going to be nonpolar. And lastly, I believe, or two more, CCl4 is going to be nonpolar because we have equal pulling in all different directions. Carbon is bonded to four identical atoms. And lastly, CH2Cl2. In this one, chlorine is pulling atoms a lot more extremely than carbon is. And so since we have them going in all different directions, it's going to be polar. So just think about those rules. If there's a lone pair around the central atom, it's polar. Or if it's bonded to different things, it's going to be polar. Those rules should help you. All right. Next, we're going to talk a little bit about intermolecular forces. Intermolecular forces, there are 3 types. The first is London dispersion forces. All molecules experience these forces. They're very, very weak forces that just hold one molecule of, let's say, water to another molecule of water.
Thank.
You're welcome.
I appreciate that.
No problem. The next type of intermolecular force is a dipole-dipole force. Dipole-dipole forces are experienced by all polar molecules. All dipole-dipole forces are a little bit stronger, and they form between the negative end of one atom and the positive end of another. So if we look at water, the water is slightly negative, the hydrogen is slightly positive, so there is a force between one and the other. And lastly, we have hydrogen bonding. This occurs, this is the strongest type. This occurs in special polar molecules when hydrogen is bonded to either nitrogen, oxygen, or fluorine. So they're the strongest forces, and they're only found in some polar molecules. And another example of this is with water. If we look at water, we see hydrogen is attached to an oxygen, and therefore there is going to be hydrogen bonding in this molecule because it's polar, and hydrogen is attracted to an oxygen. So let's again practice with these same ones. In this, we have HBr again. There are 2 types of IMFs present. The first thing we need to do is figure out that this is a polar molecule. Therefore, because it's a polar molecule, it has dipole-dipole forces. Every molecule has London dispersion forces, and we don't see hydrogen attracted to either a nitrogen, oxygen, or fluorine. Therefore, it's London dispersion and dipole-dipole. In this next problem, we've got hydrogen attracted to hydrogen. This is a non-polar molecule, and non-polar molecules only have London dispersion forces. Next, we've got NH3 or ammonia. In this one, it's obviously going to have London dispersion forces because it is a polar molecule. It also will have dipole-dipole forces. And because we have this hydrogen being attracted to this nitrogen, we're also displaying hydrogen bonding because that exists between NOF being bonded to a hydrogen. Next, we've got a nonpolar molecule here. Because we're working with a nonpolar molecule, only London dispersion forces are going to be present. Again, another nonpolar molecule. Because we have a nonpolar molecule, only London dispersion forces are present. And lastly, we have a polar molecule where there is no hydrogen being attached to a nitrogen, oxygen, or fluorine, which is indicative of a hydrogen bond. And therefore, we have London dispersion forces, which are present in all bonds, and dipole-dipole forces, which are present in all polar molecules. Now that we've practiced a little bit of that, I'd like for y'all to go to Activity 5 and do the Polarity and IMF sections for each of the 11 examples that we did the shapes of yesterday, and we'll start putting it all together tomorrow. Thanks.